This is the video solution to problem 123 by Group 16, Mark Koshman and Adam Griebel. We are given that a 2 by 2 by 2 unit solid cube, centered at the origin of coordinates, is subjected to the deformation described by the map phi of z equals z1 plus 1 over 3 a z1 cubed e1 plus z2 1 over 3 a z2 cubed e2 plus b z3 e3. We are asked to compute the values of the constants a and b that are consistent with the observations that the total volume of the block is unchanged by the deformation, and the total area of the side with original normal E1 decreases by 5% due to the deformation. Assuming that the cube is made of a linear, elastic, isotropic material with Lamé parameters lambda and mu, find the body forces and surface tractions required for equilibrium. And it is given that we can assume that the linearized strain tensor is adequate to describe the strains for this problem. Okay, so here is our deformation map given in the problem statement. We know that dV equals the determinant of F times the underformed volume. We were given that this ratio is 1, and our underformed volume is the 2 by 2 by 2, which is 8 units cubed. So that will be our new volume as well. We also know that NdA equals its determinant of F times F inverse transpose times M, which is the unit normal in the underformed state, times dA, which is the area in the underformed state. We were given that this ratio is 0.95 on the surface that has normal E1. So we know that our new area will be 0.95 times 2 times 2 equals 3.8. So we need our F tensors and also our F inverse transpose. F equals the gradient of our deformation map. You can see that here. We have 1 plus az1 squared, 1 plus az2 squared, and b and the diagonals and everything else is 0. This is a symmetric tensor, so that's also equal to the transpose. Inverse transpose, we have 1 over 1 plus az1 squared, 1 over 1 plus az2 squared, and 1 over b. For the new volume, we need to integrate that equation from earlier over all three directions times the determinant of f. And each of these dimensions ranges from -1 to 1. Here's our determinant of f, which is 1 plus az1 squared times 1 plus az2 squared times b multiplied by dz3, dz2, and dz1. After integration, we get 8b equals 1 plus 2/3 a plus 1 over 9a squared. And this is equal to our initial volume, which is 8. Solving for b, we get b equals 1 over 1 plus 2/3 a plus 1 over 9a squared. So we know that a equals the double integral over z2 and z3 of the determinant of f times the magnitude of f inverse transpose operating on m times dz3 dz2, where m is the unit normal to the face, which is E1, which is 1, 0, 0, as you see there. So the f inverse transpose m, magnitude of that will be 1 plus az1 squared. So this integral becomes, these two cancel out, just 1 plus az2 squared times b dz2, 3 dz2. Integration will give that this new area equals 4b times 1 plus a over 3, and we know that this equals to 3.8. Solving this further, we find that 0.95 equals b plus 1 plus a over 3. Substituting in our b from earlier, we get 0.95 equals 1 plus a over 3 divided by 1 plus 2/3 a plus 1 over 9a squared. Solving for a, we get a equals either -3 or 0.157895. The corresponding b are either infinity or 0.9025. B equals infinity is physically impossible, so we will go with this answer. Okay, so we've been asked to find the body forces and surface tractions. To do that, we will need the stress and strain tensors. To find the strain tensor, because we were given that we can assume that it's a linearized strain, it's equal to 1/2 of the gradient of u plus the gradient of u transpose. where u equals our deformation map minus c. So we get u equals 1/3 a z1 cubed e1 plus 1/3 a z2 cubed e2 plus b minus 1 z3 e3. Taking the gradient of that, we get a z1 squared, a z2 squared, and b minus 1 in the diagonals, everything else being 0. This is again a symmetric tensor, so that is also equal to its transpose. Because it is equal to its transpose, the 1/2 cancels out, and we get that our strain tensor is simply the gradient of u. To find the stress tensor, we have the following relationship, where lambda times the trace of E times I plus 2 mu times E is equal to our stress tensor. The trace of E is the sum of the diagonal components, so we get A times the quantity z1 squared plus z2 squared plus b minus 1. In tensor form, our S tensor looks like this. We've chosen not to write out the trace of E just to save some space. So to find the body force, we know that the divergence of S plus B equals 0. To find the divergence of S, we get 2 times the quantity lambda plus 2 mu times A z1, 2 times the lambda plus the 2 mu times A z2, and 0 in the E3 direction. This is equal to our negative B tensor. So plugging in our values for A and B, our body force vector, we get negative 0.31579 times lambda plus 2 mu z1. In the E2 direction, we get minus 0.31579 times lambda plus 2 mu times z2. And again, we have 0 in the E3 component. We're also asked to find the surface traction. So we know that T sub n equals S acting on n, where n is the unit normal vector. On the face with the unit normal E1, we have Z equals 1, Z1 equals 1. So S acting on E1 will give us lambda times the trace of E plus 2 mu A Z1 squared E1. Plugging in A and B and Z1, we get lambda times the quantity 0.157895 times 1 plus Z2 squared minus 0.0975 plus 0.31579 mu in the E1 direction. For the opposite side of the cube, where the normal is negative E1 and Z1 equals negative E1, we have that T sub negative E1 equals negative T sub E1. In the E2 direction, our equation is exactly the same, except that where we had Z2 in the first case, we now have Z1. And again, on the opposite side, it's just the opposite value. For TE3, where Z3 equals 1, we have lambda times the trace of E plus 2 mu times B minus 1 E3. Plugging in A and B, we get lambda times the quantity 0.157895 times Z1 squared plus Z2 squared minus 0.0975 minus 0.019, 0.195 mu in the E3 direction. And again, for the opposite face, it's just the opposite value. So we were given that we could use the linear assumption for the strain tensor, but if we were not able to, we just kind of wanted to go through how that complicates the problem. So we know that E equals 1/2 C minus I, where C equals F times F transpose. So that would give us A Z1 squared plus A squared Z1 to the 4th over 2, and then A Z2 squared plus A squared Z2 to the 4th over 2, and then B squared minus 1 over 2. So you can see that our strain tensor has it has a whole bunch of extra terms here that really complicate the problem. In most small deformation cases, these will be very small, and so when it's to the power of 4, it becomes negligible. But again, our stress tensor would be using the same formula as before. We'd have lambda times the trace of E plus mu times 2A Z1 squared plus a squared z1 to the fourth lambda times the trace of e plus mu times 2a z2 squared plus a squared z2 to the fourth, and then lambda trace of e plus mu times b squared minus 1, which again is much more complicated.